with chapter 16 of thermodynamics. So last time we had a big giant lecture of like 10 minutes, and but we're talking about entropy here in this chapter to begin with. And remember that entropy is delta S, which stands for the change in entropy, and it has to do with the amount of disorder there is. It's oftentimes thought of. And entropy is a little bit different than some of the things we sort of think about. In the case of increasing disorder or decreasing order, however you want to think about it, the delta S value does become more positive. And as the amount of disorder decreases, which would mean the amount of order increases, the delta S value there will be negative in that particular case. And we talked about changes of state as a very easy way to sort of visualize, kind of the increase in disorder or decrease in disorder. As we go from solid, which is very, very ordered, you would expect a more negative sort of entropy. As you go from, say, solid to liquid to gas, the entropy should be increasing, and those changes should result in a more positive value for entropy. Entropy, again, is in terms of units, a little bit different as well. It typically is given in joules. We also refreshed a little bit about enthalpy, which is what you talked about in Chem 50 probably, and that is the delta H value, and that's really sort of the heat of a reaction. And a reminder that delta H values, again, that are negative are exothermic type processes, which means heat and energy is released, while our delta H values that are positive are endothermic reactions, which means heat and energy is absorbed. And as we talked about sort of at the beginning of this chapter, although exothermic reactions do sort of favor spontaneity, it doesn't necessarily guarantee it, as we saw some examples of some endothermic reactions that are also spontaneous reactions. And a reminder that, again, when we're talking about spontaneous reactions here, we're really not talking about anything in terms of the speed or the rate of the reaction, which again is basically kinetics. It's basically just saying that under these conditions, we would expect this reaction to occur. And again, it could be really fast or it could be really slow, but it will occur based on the information in the problem or whatever it may be. So again, when we say it's spontaneous, it has really nothing necessarily to do with the rate of the reaction. The enthalpy as well in terms of units are in kilojoules typically. And again, we're going to see an equation where both of these guys are sort of involved. So you always want to make sure that you're not off by a factor of 1,000. You got to do some type of conversion usually. So we can't use sort of entropy sort of individually of the reaction to determine whether or not a reaction is spontaneous. And where we left off was the idea that we could use what is referred to as the entropy of the universe to help us decide whether or not a reaction is going to be spontaneous. So if you calculate the delta S of the universe and it is greater than 0 or really a positive number here, it is going to be a spontaneous reaction. Obviously, the opposite is true. If you were to calculate and got a negative number, it would be a non-spontaneous reaction. In an equilibrium process, the entropy there will be 0. Again, really, because there's kind of nothing happening in a sense. The rate of forward and reverse reaction at equilibrium is basically equal to each other. So everything is pretty much balanced at that point in that sort of process. Now, individually, when we talk about the system, sometimes it is also referred to as like the reaction, because that is typically, right, in chemistry, sort of what we're interested in. And obviously the surroundings are opposite of that. So adding those together will again give you the delta S of the universe, which you could then use to determine whether or not a reaction is spontaneous. There are actually two different ways that we calculate each of these. And I think that's where we left off. So that is where we're going to pick up here. We're going to first talk about how we go about calculating the delta S of the system or the reaction, which is essentially kind of the same thing. So we could calculate the standard enthalpy or entropy of the reaction. By the way, when you see like the little knot there, if you will, That usually means sort of standard conditions. That usually means table type conditions. And what those table type conditions usually are is usually at temperatures 25 degrees Celsius. If you're dealing with any type of gases, everybody's at 1 atmosphere. And if you're dealing with any type of molarity or concentration, everybody is 1 molar. So those are typically the standard conditions. And when you see those little kind of knots on things, delta H naught or delta S naught and so forth, it usually means standard type conditions. Also usually means you kind of go to the table a lot of times and get those values from. And that is basically how we calculate the delta S of our system. We pretty much go to a table, and if all we're given is just a reaction, we add up all the delta S values that we find in the table for our product side. We also do need to multiply by the coefficients. So, you know, if C was a 2, we would need to take 2 times the value of C that we would find in the table and so forth. We would then subtract it from all of our reactants, doing the same thing. We want to multiply the values that we find in the table for delta S, and we want to multiply it by the coefficient by the values in the table that we find for delta S. And again, this is sort of our state function. Again, products are final state, right? Initial state being our reactants. So where we start and where we end are really the most important things here. Now, when you go to the delta S table there in the book and you look up these things, as we talked about, you do want to make sure that you find not only what you're looking for in terms of the substance, but you also find it in terms of the actual state it is in. The other thing is typically delta S values will all be positive in that table. And again, they are in units of joules. And something that's different than delta H is for delta S, you will find values for things like O2 and things in their natural state. Again, for enthalpy, you will not. They will typically be 0. So why don't we try one here? And this is the reaction. I think it's on your notes, but I'm missing one up here. It is for CO2. What was that value? It is. Thank you. 213.6 joules. There we go. All right. So take a second and calculate that. And obviously, these would be the values that we would find if we went to the table, obviously, and looked up these values. Let's take a look at it. So once again, to calculate the delta S of our reaction or system here, it is the delta S of our products minus the delta S of our reactants. Once again, in this type of problem, you're probably will just be given the equation. You got to go to the table. Usually in the back of the book, you can find a thermodynamics table that has all these values in it. So to calculate that, we will take our delta S and we will start with our products. So we do have 2 of the CO2. So we need to take the coefficient and times it by the value we would find in the table. That takes care of all of our products. We would then subtract it from our reactants. 2 times the value of CO, which would be 197. And we would also add it, since we have 102, would just be one of those guys there. And it looks like if we do all that, I'll go above it, maybe a minus 170 something, I think it was, right? 2 times 213.6. It's like a minus 173.6, we'll call it. And these are joules here. First off, any question on the calculation? So this value alone, once again, does not tell us whether or not this reaction is spontaneous, but the value does tell us what is going on in this reaction. Am I increasing or decreasing the disorder here? The amount of disorder here is decreasing, right? It has a negative value for delta S there for the reaction. That is when you decrease the disorder, or opposite of that, increase the order, right? Something becomes more ordered. Now, you could actually, if you just look at the equation, make a pretty good guess of what your value should be, not in terms of a number, but in terms of whether or not it should be positive or negative. When we look on our reactant side, we have 2 gas molecules and 1 more there. That is 3 gas molecules. When we get to the product side, we got a grand total of 2 gas molecules. So in this particular reaction, we are going from a situation of 3 gas molecules to 2 gas molecules. So if you just think about it logically, you got 3 things flying around, that's a lot of disorder. If you just drop it down to 2 things, we have a little bit more order happening here, and we're increasing the order. So just by looking at the reaction, in this case, since we actually yielded less gas molecules than we started with, we could predict that this should be a negative value for our delta S of the reaction. We're increasing the order, or again, decreasing the disorder. Any questions on that? So these are good things to think about when you do your calculation. Again, it won't help you with the number part of it, but it will help you with the sign part to make sure obviously the sign sort of makes sense. Any questions on how to calculate this here? Okay. So as I mentioned just a second ago, by looking at the reaction, you can make a prediction as to whether or not you expect that to be positive or negative value. If the opposite was true than what we just did there, if we actually did produce more gas molecules than we started with, we again would be creating a lot more disorder. So more gas things flying around, causing a lot more disorder. And we would expect the actual delta S value to be positive in that case. Obviously, the second thing there is what happened in the example we just did. We actually had less gas molecules at the end than what we started with, increasing the order. And if there's really no change in the gas molecules, you would probably have a relatively small change in the entropy, and it could be positive or negative. So based on that and this reaction that we see on the bottom, would we expect it to be a positive or negative value for the delta S of the reaction here? This one should be negative here, right? We are starting on this side with 1 gas molecule, and we are ending on this side with no gas molecules. So we got one little thing flying around, which is annoying, right? And it causes a lot of disorder. And you get rid of it, then obviously it causes a lot more order in this case. So yeah, because of that, we would expect this guy to be negative. And you will get a lot of questions like that in this chapter. Sometimes they won't really give you a lot of numbers. They'll just kind of ask you, what do you think will happen based on the reaction? So a lot of these times you could kind of analyze the reaction and make a pretty educated guess as to what's happening. So this is how we calculate the delta S of the system, or the reaction products minus reactants. Basically look it up in the back of the book in the table to get each of those values. Let's then talk about the surroundings then, and sort of what is happening in a surrounding situation. On the left-hand side is an exothermic reaction, which means our system is sending out the heat and energy to our surroundings. So if the system is giving off energy to the surroundings, would that make the surrounding molecules move slower or faster? They probably would move faster, right? They're gaining that energy, which means the amount of disorder in the surroundings, should that go up or down? So if everybody in the surroundings gains the energy and they start flying around a lot faster, that should increase the disorder, right? And we should see that the result there is our delta S of our surroundings will become a positive value because it's gaining all that energy from the reaction. Opposite is true here under sort of normal conditions here. If we have an endothermic reaction, the guy on the right, the energy is actually going into the system. The result of that is all the surrounding molecules are going to lose energy, which means they're going to basically slow down, right, and not be moving around as fast. The result of that is we should start to see for the surroundings the amount of order increase, the amount of disorder decrease, and that would result in a negative value here for our endothermic process in terms of the surroundings. So there is sort of an opposite relationship that we see. The delta S of the surroundings is proportional. That's what the little symbol is supposed to be there, a proportional symbol, to negative the delta H of the system. So if we just kind of sketch those up here, delta S of the surroundings. Question?
Is it how the surroundings are losing heat and getting heat to the system? It's kind of like how you do that.
Yeah, so if your question is that in an endothermic process, that's what would happen. The energy would go from the surroundings to the system. in terms of the surroundings, everybody would kind of slow down a little bit, become a little bit more ordered because they're losing that energy. It would be obviously opposite there for the system. The system would actually be gaining the energy, and we expect to probably an increase in the amount of disorder. So a simple example of that would be like an ice cube, right? Ice cube will pick up energy from the surroundings, right? Surroundings losing that energy, becoming a little bit more ordered, but the ice cube, as it picks up that heat energy, will start to melt, right? And now the system, which is our ice, has now become solid to liquid, which means more disorder, and it would increase in terms of that. So there's sort of an opposite relationship in terms of that transfer of heat that's going to cause that. And that's why our delta S here is going to be negative of our delta H of the system or the reaction. So that means if I have a exothermic reaction, right, my delta H value should be positive or negative. Delta H should be negative, and since this relationship is negative of my guy there, 2 negatives gives me a positive value, right, for our surroundings, and opposite is true for an endothermic reaction. Negative endothermic would be a positive value. Negative and positive value gives you a negative value here for our surroundings. So there's sort of that opposite relationship. Now, does the temperature of the surroundings make a difference in terms of what you would see? And the answer is it does. So for example, you know, if we lit just a match out here in the open, you could feel the heat, right, coming off the match and all that, right? If you lit a match and you had your oven on to the highest temperature it could go, and you had the match inside the oven, there probably wouldn't be that much of a temperature difference change. By the way, don't do that. Don't crawl into your oven with a match or anything like that. But obviously, if your temperature inside is very, very hot to begin with, you light one little match and you have that heat coming off, is not going to basically make a tremendous amount of difference in terms of the surroundings there, because there's a lot of energy out there to begin with. So under sort of normal conditions, normal temperatures and stuff like that, we do see this sort of opposite relationship. But if you do have maybe some extremish temperatures happening there, some really high temperatures, even maybe some really low temperatures, you know, the change that you see may not be all that much of a change in terms of the entropy. Any questions on that there? All right. So as I mentioned before, again, the temperature of the surroundings, it does play a role in that, but under most conditions, we're talking about sort of normal-ish temperatures. And under normal temperatures, we will see that opposite change occur. Now, to calculate the delta S of the surroundings, everything got a little shifted here, so I think it's okay on your handout there, but delta S of the surroundings is equal to minus delta H of the system or reaction divided by the temperature in Kelvin. So that guy's got to be in Kelvin. Now, this equation that we see here will look very much like an equation we will see later, but it has a negative here. So if you're using this equation, it should have a negative. Later on, we'll find an equation that looks very similar without the negative. But this is how we would calculate our delta S of the surroundings. Taking this along with our delta S of the system or reaction that we just did there, delta S of our products minus the delta S of our reactants, that will once again allow you to calculate the delta S of the universe there, which would be our delta S of our system plus the delta S of our surroundings. Now, a couple of things here. This guy here probably will be in joules, since you're going to go to that table and pick it up. That's a bad J there. It's a fancy J. Delta H here is typically in kilojoules. So at some point when you put these two together to add, you want to make sure that you are in the same units. Otherwise, again, you're going to be off by that factor of 1,000 if you leave that guy in kilojoules. You can convert them both to kilojoules, you convert one to joules, whatever you like to do, but you do have to do some type of conversion. Personally, I go with joules. That way everybody's kind of in the right units for delta S, but you do have that difference in sort of units that you want to be careful of as well. Now, if you were able to calculate both of those things, the system and the surroundings, you could put it together for the universe there and figure out whether or not this reaction would be spontaneous. Any questions on that there? So why don't we try one here and see what we come up with. For this reaction here, the delta H is given to you. And again, these are our table values down here for our delta S. Why don't you calculate the delta S of the system, the surroundings, and perhaps the universe would be good as well here. And determine whether or not this reaction is going to be spontaneous. So take a couple minutes, see what you come up with. Just 3 things. Okay, let's take a look. So I'm going to start with the system here. So we're basically just going to do our products minus reactants, so we can find those values there in the table. So we do have 2 of the NH3, so we want to take 2 times the value of NH3, which is 193. That takes care of our products. On our reactant side, we got 1 times the value of N2, which is 192. Plus our other reactant, which is H2, and there's 3 of them. So we want to take 3 times 131 there. And looks like a minus 199 joules here would be our delta S of the system. Any questions on that there? Now, does this make sense based on the equation? If we look at the equation, remember that this will not tell if it's spontaneous or not, but we are starting here with 4 gas molecules and we're ending with 2 gas molecules. So the number of gas molecules here has decreased, which means we are increasing the order, decreasing the disorder, and we would expect the reaction to yield us a negative value like it did there. So that's all good in terms of logic. At this point, we can then calculate our delta S of our surroundings, which is minus the delta H of the reaction, divided by the temperature here. We do need to convert our temperature into Kelvin, so adding a 273 should give us a 298 Kelvin. We're going to put that in here. We're going to not forget the negative. That is part of the formula, so we do need that negative. And it is also negative here, 92.6. I personally am going to multiply it by 1,000 just to convert it into joules at this point for me, so everybody will be in the same units. Obviously, if you did not, you would still be in kilojoules at this point. We're going to divide it by 298 there. And that will yield me here for my surroundings. If I hit the right number there, try that. Times 1,000 divided by 298 gets me about 311 joules here. Question on that one there. Obviously, if you left it in kilojoules, you're probably looking at like 0.311 at this point. Yes. Also makes sense, right? Because this reaction is exothermic, right? Which means the surroundings should be picking up that heat and energy, which means for the surroundings, we should actually be increasing the disorder, and we should see a positive value there for our surroundings, which we also do as well. Any questions on that there? Now, to get to the part of whether or not it is sort of spontaneous or not, we got basically everything we need here. We just need to add them together. So the delta S of the universe here will be our minus 199 joules plus our 311 joules. Once again, because I did the conversion earlier, I'm good on units. If you left yours in kilojoules, you do need to do a conversion at this point to get everybody to the same units. So minus 199 plus a 311 looks like a $1.12 left over there. And our delta S of our universe here is a positive number, which means, is this reaction spontaneous? It is spontaneous because, again, the delta S of the universe here gave us a positive number. Any questions on that? This is actually a really good example of a spontaneous reaction, which is super slow if you don't put a catalyst in it. Yeah, but it will happen, but very, very slow. So they oftentimes add a catalyst to this reaction to speed it up. Any questions on any parts of the calculation? So again, we could use our entropy here and our entropy of the universe, if possible, to calculate it to determine spontaneity. But there is another way that we could look at another sort of thermodynamic property that helps us understand whether or not a reaction is spontaneous. But before we get there, let's talk about the third law here of thermodynamics, which is the entropy of a perfect crystal substance is zero. Again, if we looked at that sort of Boltzmann equation that we saw earlier, obviously if you had a perfect crystal, there's probably one way to be perfect, and that means our microstate there would be 1, making this into a 0 and gives us an entropy of 0. As we talked about, obviously, as you go from solid to liquid to gas, there is an increase in the entropy, becoming more positive as you go that way, obviously opposite if you go the other way. What we're looking at here is an entropy versus temperature. You may also remember like a heating curve that you learned in 50, I imagine, where you had something that is like this curve, but opposites. And let's just say this is, say, for water here. This would be 0 degrees, right? And this would be 100 degrees Celsius for water. This would be ice down here, right? Liquid water kind of in the middle. And this would be steam or gas up there on top. These are phase transitions that occur, right? And when something goes from solid to liquid or liquid to solid, that is either the normal melting point or boiling point, not boiling point, melting point or freezing point. Does that occur at the same temperature or different temperatures? The freezing point and melting point, is that the same temperature or different temperatures? It is the same temperature, like 0 degrees Celsius right there. So right at 0 degrees Celsius, for example, for water, you got a little bit of ice and some liquid sort of happening in equilibrium with each other. Same thing at the boiling point, the transition between liquid and gas happens at the same temperature. The only difference is what you're doing in terms of energy. You're putting energy in, you're taking energy out. It's not until you get a little bit above 0 degrees Celsius, you have liquid water, for example, not until a little below 0 degrees Celsius that you have ice. But right at 0 degrees, you have both phases in equilibrium. You might also remember that there's a certain amount of energy to do this transition. Yes, that is the delta H of, not everybody at once. Yeah, it's just that's delta H of fusion is a good answer there. That's the delta H of fusion there, or the heat of fusion is sometimes referred to. And that is the energy required to do nothing more than take a substance from solid to liquid or liquid back to solid, not change the temperature, but basically change the phase. For example, water at 0 degrees Celsius is when that occurs. It is roughly 333 joules per gram, or 6.02 moles, kilojoules per mole, if I wrote that right. And that's the energy required to do that. The number is the same. The sign is different depending on which way you're going. Obviously, if we're going from solid to liquid, it is plus 333. And if we're going the opposite way, it's an exothermic process, minus 333 to go that way. Same thing happens here as we transition from liquid to gas. That's the delta H of vaporization. Yes, so the delta H of vaporization, or the heat of vaporization. And that's the energy or the heat required to go from liquid to gas or gas back to liquid. Once again, happens at the same temperature. Sign's just different. And once again, specifically for water here, you're looking at about 2260 joules per gram, or roughly 40.6 kilojoules per mole, give or take a joule or two, is the energy. And again, same idea as we go from liquid to gas, that's a plus 2260. And opposite would be exothermic, minus 2260 joules per gram. That's the energy, again, required to basically just change the phase in that. And there's entropy that goes along with that. There's the delta S, as we'll talk about here, of fusion, which is the entropy change that occurs as you go from solid to liquid and liquid back to gas. And obviously a delta S of vaporization, which is that energy change that occurs when you go, the entropy change that occurs when you go from liquid to gas or gas back to liquid. Now, by the way, when we're looking at a graph like this and we're doing like this move over here, how we calculate the energy for that anywhere in that green line. That's all liquid, yes. Temperature changing, but the thing stays the same phase. If I wanted to calculate the energy, anyone? Q equals ms delta T, a little specific heat. Nobody see that equation? Uh-oh. All right, we'll take a field trip to Chem 50 later, but so anywhere on this curve where you're basically changing the temperature, but the phase stays the same. If you want to calculate the energy, you use a specific heat equation to do that, which might pop up as some of these thermodynamic type things. And by the way, in case you're not sure, M is mass, and that is in grams. Delta T is the change in temperature. I'll write down here. Delta T is the final minus the initial. S is the specific heat capacity. It has units of joules per gram per degree Celsius or calories per gram per degree Celsius. You know, that is the number. Maybe this will jog your memory, 4.184. Yes. Okay. So you learned it there somewhere. It's in there. And that is like you did some calorimetry cups, some coffee cups, threw some stuff in there with a thermometer or probe. Yeah. So that is specific heat for liquid water, by the way. And obviously the mass is usually in grams here. So if you ever had to calculate the heat or energy in a process where basically, again, it stays the same phase, but does change the temperature, specific heat's usually the one that you want to use. If we're talking about energy of just changing the phase of something, but not the temperature, is usually a delta H of fusion or a delta H of vaporization. And obviously there's entropy changes that occur as those things occur as well. Last thing here as well is, as you can see from my graph there, it takes a lot more energy to go from liquid to gas, right? As more than it does to go from solid to liquid. And that's because obviously as you go from solid to liquid, everybody's still together pretty close to each other, right? As you go from liquid to gas, it has to completely break apart from each other. So you need a lot more energy to do that. And that's why you see, like, for example, for water here, the difference in the number of, there's only 333 joules versus like 2200 joules to do the same thing at the boiling point. Okay, so there is another thermodynamic value that's important for us, and this is what is referred to as Gibbs free energy. It is a different letter in the alphabet, which is delta G here. And delta G does, I know it kind of looks like a 6, but it's kind of like a G. The delta G here is Gibbs free energy, and it's basically energy that's available to do some type of work. So as we just saw there, we could use our entropy to help us out. We could actually use delta G to sort of directly decide whether or not a reaction will be spontaneous or not. If we do calculate the delta G and it is negative, it will be a spontaneous reaction. If we calculate the delta G and it's positive, it will be a non-spontaneous reaction. This is one of maybe 3 or so different ways that you could calculate the delta G for a particular reaction. My advice would be to calculate it based on the information given to you. So in this equation, we could calculate the delta G. It's equal to the delta H of the reaction minus T, which is our temperature. Obviously, it does need to be in Kelvin here, times the delta S of our system. This equation here is a good one to use if you're obviously given the delta H value and the delta S value. You could just plug it into this equation and use it. This is also one where you need to watch units. Again, here your delta S will be in joules. Delta H will be in kilojoules. So once again, you need to do the conversion whichever way you want to go. A lot of times though, delta G is given in kilojoules. So that's sort of a common sort of unit for delta G. And once again, if we do calculate the delta G of the reaction and it is a negative number, it is going to be spontaneous the way the reaction is written. Reactants go into products. If you calculate it and it is a positive value, what that means is the reaction as it is written is non-spontaneous. But if you reverse the reaction, it would then become spontaneous. Much like delta H, right? If you reverse a reaction, the sign changes. Same thing happens here. If you reverse a reaction here, the delta G value sign will also change. And that's why the reverse reaction would be spontaneous. And if you have a delta G value that is equal to 0, you are at equilibrium at that point. So again, this is one way you can calculate Gibbs free energy, delta H minus T delta S. Another way, which is like all the other thermodynamic values, is you essentially could do products minus reactants. So once again, you could go to the table, look up your delta G values for everybody, sometimes referred to as the delta G of formation, or the standard energy of formation. And it basically is just like everything else. Delta G naught would equal our delta G of our products minus our delta G of our reactants. You would do the same thing as everything else. You have a coefficient, you need to multiply it by the value that you find obviously in the table. Also, very much like delta H, anything that is in its free sort of stable state will have a delta G value of 0. So really the only thing that will have a value for things like O2 and N2 and things like that are delta S values. And as I talked about just a second ago, this is really the meaning there of sort of standard conditions is what we have going on under these when you kind of see the little circle there. Again, 1 atmosphere, 1 molar for concentrations, and the temperature is 25 degrees Celsius. All right, so why don't you give this a go here? You got your delta G values from the table at the very bottom. Okay, let's take a look. So once again, if this is sort of the problem and this is all that's given to you, don't reinvent the wheel and calculate H and S and use the other equation. When you could just go to the table, obviously, and do products minus reactants directly from the delta G values. So that's what we'll do here. We'll do our delta G will equal our products, which is 12 of the CO2s times the value of CO2, which obviously we would get from that table. We would then add it to 6 times the value of water, which once again would also come there from the table. And that would take care of our product side. We would then subtract it from our reactant side, which would be 2 times our 124.5 and add it to basically 15 times 0 here. And doing all that good stuff there. Looks like a minus 6405 kilojoules here. First off, any questions on the calculation? That means our delta G is negative. So is this reaction spontaneous? This reaction is spontaneous. Again, we got ourselves a negative delta G. So that is all you need to know in this situation. Any questions on that there? Now, looking at the other equation, our delta G is equal to H minus T delta S. We could just look at the equation and the sort of signs, if you will, of H and S, and we can make a pretty good assumption as to whether or not we would expect a reaction to be spontaneous. So, for example, if we had a endothermic H, which would be positive, and we had an increase in entropy, which would also be positive in this case. The only way that this reaction would be spontaneous is at very high temperatures. And that is because, remember, this guy's kilojoules, this guy is joules. So the guy over here has basically a 1,000-fold jump, if you will. So the only way to get this guy larger than the other number, right, is you would need a very, very high temperature to do so. So under low conditions or normal sort of temperatures, you will find this reaction to be pretty much non-spontaneous at this point. Again, because this part will not be big enough to overtake the other part and make delta G negative. If we had a negative delta H in an exothermic reaction. We'll change that guy to negative. Now what we got going on is our guy here is going to be negative, and this guy at normal small temperatures will be pretty much positive. And that means that we will end up with a negative temperature, a negative value for delta G at any temperature possible. Because even if this guy got larger, our first guy is negative and this guy is negative, so you're going to end up with a negative value at any temperature. So in that situation, negative H, positive S will always result in a spontaneous reaction regardless of temperature, because the delta H really is negative. Now, if the delta H is negative, but our entropy becomes negative as well, which is this box right here. And if this guy is negative, that negative here for delta S is going to turn our back number into a overall positive value, right? Because negative and a subtract button there will give us a positive value. That means that at low temperatures, we will get a delta G that is going to be negative, because again, this will not be big enough to sort of overtake it. At really high temperatures, that will be enough for that guy to overtake it and become a positive number, but at low temperatures it will not. And lastly here, if we end up with a blank screen, if we end up with a box on the bottom left there, where we end up with our delta H being positive and our delta S here being negative. Once again, that negative here is going to turn this negative into a positive number, which means no matter what temperature you're at, you're going to end up with a delta G that's going to be positive. And the reaction would not be spontaneous at that point. So there's two situations where no matter what you do with the temperature, you're kind of locked into it being spontaneous or non-spontaneous. Delta H is negative and S is positive. You're going to end up with a delta G that's going to be spontaneous at any temperature. And again, the opposite there, which would be this box here. So like I said before, there's a lot of questions sort of like this where they'll just go, hey, the H is positive, this guy is negative. Do you expect this guy to be a spontaneous reaction or not? And they really don't give you numbers. So you can just make up numbers and kind of throw them into the equation and see what you get. But this is a good way to sort of predict what you would expect to occur. So let's talk a little bit about spontaneity and temperature and some differences here. So for example, if we did this reaction of calcium carbonate going through a decomposition reaction, and let's just say we did this at 25 degrees Celsius, is this reaction spontaneous at 25 degrees Celsius? So basically calculate the delta G value here and see what you come up with. So take a second there and calculate that delta G. We are given the H and the S, so this would be a good place to use that equation we saw earlier, delta H minus T delta S. Obviously, we will need to convert that into Kelvin, which would be 298. So putting our numbers in here, I'm going to take my delta H value, which is 177.8. Once again, I'm going to multiply it by 1,000 to convert it into joules, because we do have different units here. Minus our temperature, which is 298 Kelvin, times our delta S, which is 160.5 joules here. And if we do all that, we end up with a roughly 1,29971 joules, or about 130 kilojoules would be our delta G value for this reaction at 25 degrees. First off, any questions on the calculation? Again, you could convert your delta S into kilojoules and roll that way, and you should get hopefully the same number at the end there. Is this reaction spontaneous? At 25 degrees, it is non-spontaneous here at 25 degrees Celsius. So can we figure out sort of at what temperature this reaction would become spontaneous. And the answer is we can use the same equation here to help us decide at what temperature this reaction would become spontaneous. We do know that in order for it to become spontaneous, delta G needs to be a negative number. And usually a negative number is at the left-hand side there of 0, or the south side of 0. So we could take that equation and set delta G equal to 0. And that would give us delta H minus T delta S. And if we're interested in our temperature, we could take that whole thing over here and solve for our temperature, which would be our delta H divided by our delta S value. And we have both of those numbers given to us, so we could actually plug those in. And once again, I'm going to convert it into joules, so they're in the same units. So I'm going to multiply by 1,000. We're going to divide it by the 160. And if we do that there, we get 177.8 times 1,000 divided by 160.5. We'll call it about 1108 Kelvin, which if we subtract 273 from gets us roughly 835 degrees Celsius. This number would represent the minimum amount of temperature that you would need to turn this guy into a spontaneous reaction. That's quite hot, I'm assuming. So, and that's what we actually see here if we look at this graph. This graph is the pressure of CO2 versus temperature in Celsius. And we can pretty much see that we have no pressure for CO2, which basically means that this reaction is not going this way. The only way we could get pressure is to actually make some products, right? Because the CO2 is on the product side. And we really don't see, technically speaking, until about 835, some pressure occurring there for our CO2, basically 1 atmosphere of pressure. We do get a little bit of it before, but really not until we get to sort of standard 1 atmosphere conditions. It doesn't occur until about 835 degrees Celsius. So we could actually use this equation if we happen to come across a reaction that is non-spontaneous, and we could actually solve for temperature, and that will give us sort of the minimum temperature that this reaction would become spontaneous. Any questions on that? Now, does this make sense based on what we were just talking about by just looking at this equation? And hopefully it does. So let's see. We had a positive delta H and a positive delta S, which means in order for delta G to become negative, this back part here has to become a higher number than the front part. And the only way that could occur is at a very high temperature. And I think 335 does qualify as a relatively high temperature. Any questions on that? Obviously, at a normal temperature, like we saw with our original calculation, that temperature of 25 degrees was not big enough here to make that part a larger number than our delta H. And then we ended up obviously with a positive value. Any questions on that there? Okay. All right, so give this a try here. For the following reaction, delta H and delta S are given to you. Are the reactants or products favored under these conditions? Again, we have delta H and delta S given to us, so might as well use the equation that has both of those in it. So putting in our numbers here, and just like I've been doing, I'm going to convert this first one into joules. So I'm going to multiply it by 1,000. We also obviously want to convert our temperature into Kelvin here. So that's a 273 plus that gives us a 298. And our S, which would be minus 216.4 joules. That will yield us here minus 1204 times 1,000 minus 298 times negative 216.4. Looks like, I think, minus 1139512.8 joules. are roughly minus 1140 kilojoules, give or take. Any questions on that one there? Here. Yeah, so that means we have a delta G that is negative, which means reaction is spontaneous. And if it's spontaneous, that means that basically as the reaction is written, it is going towards the product side, and we would favor, in this case, products. It would, yeah. So the way it's written, it would favor the reactant side. So sometimes some books will use kind of weird wordage like, yeah, it's non-spontaneous the way it's written, but it's spontaneous in the reverse direction, which is a lot of ways of saying the same thing. It's basically going to hang over there on the reactant side, or reactants will basically be made. Yeah. Other questions? So let's talk a little bit about, and we talked about a second ago, sort of Gibbs free energy and phase transitions. So what happens in phase transitions, as we talked about, is we are changing the phase of a substance, but we're not really changing the temperature, and that is an equilibrium process. So as we talked about, delta G is pretty much going to equal 0 in an equilibrium process, which is our phase change. And again, here, this would be our liquid going to gas at that flat point. And if we put in our numbers here for the entropy, this would be basically the delta H of vaporization for water. That is water's normal boiling point, right? Water boils at 100 degrees Celsius plus a 273 gets you a 373, right? So that's the normal boiling point there of water. And we would end up with an entropy value here of 109 joules. And that does make sense in this process of it going from obviously liquid to gas, right? We are increasing the amount of entropy, and we would expect a positive number. This is, again, what is sometimes referred to as the delta S of vaporization. The entropy of vaporization in this case would be 109. Now, what happens, I was specifically talking about the process where we go from steam back to liquid water. How would this calculation change? The only difference is as we go from gas to liquid, it is a exothermic, right? Which means my delta H of vaporization should be a negative 40.79 divided by my 373, which would give me the exact same number, except that it would be a negative value. And that would make sense going in that process, right? Because we're going from gas back to liquid, which is a more ordered event. And we would expect the delta S in that case to give us a negative value. And that's where the negative would come from, is actually the delta H value that we see here. Any questions on that there? So you can use this to calculate delta H of vaporization, delta S of vaporization. Delta S of fusion would be the same type of deal, right? Except that it would be the melting point and freezing point that would happen in this particular case. Any questions on that there? This equation here, once again, is very similar, for example, to the delta S of the surroundings, which is negative delta H over T. So if we're calculating the delta S of the surroundings, you need that negative. If you're doing something like delta S of vaporization or fusion, you don't have the negative. So this is the one where, you know, sometimes people throw the negative in there for good luck, and it's bad luck because you'll get the wrong answer here. So negative only for if you're calculating delta S of the surroundings. If you're doing some type of phase change where you're using this equation essentially to get to that formula, there is no negative that's involved in there. So that's a very common mistake sometimes people will make. Any questions on that there? All right, so I want you to try one. The enthalpy of vaporization for mercury is 58.5. The normal boiling point is 630. What is the entropy of vaporization for mercury? The enthalpy of vaporization, which is the delta H of vaporization, specifically for mercury, which obviously is a different number than the one for water. That is the normal boiling point. So once again, we are really deriving sort of our equation from here because this is an equilibrium process. That would equal 0. Rearranging once again will give us that the delta S will equal our delta H divided by T. Once again, here, no negative in here. Putting this into here will give us 58.5. I'm going to once again just kind of convert it to joules. So I'm going to times it by 1,000 and divide it by our temperature, which is already in Kelvin. So that's nice. 58.5 times 1,000 divided by 630. Going to give us, it looks like a 92.9 joules. And that is a positive number with the assumption here that we are going from liquid to gas in this case. Just like in the water example I asked about just a second ago, if we were specifically said going from gas back to liquid, again, the only thing that would change would be we would have a negative value here, which then would obviously give us a negative value on this guy. And again, that would make sense kind of going in that direction. Any questions on this or anything we talked about here today? All right, we will stop there